students, welcome to the second lecture in permutations and combinations. I think you have watched lecture 1, else go back to lecture 1, watch it completely and then you can come back to lecture 2, else you cannot understand lecture 2. Anyway, these are the topics that we have discussed in lecture 1. So we have discussed about the difference between ordinary brackets and braces. We have discussed about fundamental principle of counting, both addition and multiplication. We have defined factorials, we have defined linear permutation and circular permutation, and we have discussed about the differences between linear permutations and circular permutations. And then we have this following results. Number of permutations of n distinct objects taken are at a time. In general, it is denoted by NPR, and we have given the formula for NPR, which tells us how many linear permutations we can form using n distinct objects taken r at a time. Anyway, let me elaborate these things once again. So, when order matters, we are going to use these brackets. If we use these brackets, then order does not matter. And then we have discussed about fundamental principle of counting, both addition and multiplication. So if a task T can be performed in two ways, W contains two different works. If a task T contains two different works, W1 and W2, and W1 can be performed in M ways and W2 can be performed in N ways, then the number of ways of completing the task is equal to number of ways of completing W1 times number of ways of completing W2, which is equal to M times N. And similarly, if a task T can be performed either in W1 or W2. So in order to complete the task, we have two formats, W1 and W2. Then the number of ways of completing the task is equal to number of ways of completing W1 plus number of ways of completing W2, which is equal to M plus N. So whenever end comes, you have to multiply, and whenever R comes, you have to add. And then we have defined factorials. So n factorials are defined for non-negative integers, and we define n factorial like this. N factorial is equal to n times n minus 1 factorial. So if I want to define 5 factorial is equal to 5 times 4 factorial, or else we can expand it again, which is equal to 5 times 4 times 3 factorial, which is equal to 5 times 4 times 3 times 2 times 1. And by convention, we define 0 factorial to be equal to 1. And then we have discussed about linear permutations and circular permutations. Linear permutations means we have to arrange things in a row. Circular permutations means we have to arrange things in a circle. A, B, C, D. So this is an example of a linear permutation. Whereas if you arrange A, B, C, D on a circle, this is A, B, C, and D. And this is a circular permutation. This is a linear permutation and this is a circular permutation. And the difference between linear permutation and circular permutations are, in a linear permutation there is a notion of first place, second place, third place and last place. But in a circular permutation, there is no notion of first place, second place or last place. So I can treat A as the first element, or I can treat B as the first element, I can treat C as the first element, or I can treat D as the first element in this circular permutation. But here in this linear permutation, I have to treat A as the first element and B as the second element. Okay, and a few linear permutations result in a circular permutation. And then we have derived a formula for this one. Number of permutations of n distinct objects taken are at a time. In general, it is denoted by NPR, and we have the formula for NPR. NPR is equal to n times n minus 1 times n minus 2 and so on up to n minus r plus 1. So this is the theorem result, and we have modified this result. So after modification, we can write NPR as n times n minus 1 times n minus 2 and so on up to n minus r plus 1. We can modify this by multiplying and dividing it by n minus r factorial. So if you multiply this and divide by n minus r factorial, it's going to be n factorial upon n minus r factorial. So this is the formula for NPR, that is number of permutations of n distinct objects taken r at a time, is equal to n factorial upon n minus r factorial. And by convention we define NP naught to be equal to 1, and NPN turns out to be n factorial upon n minus n factorial, which is equal to n factorial upon 0 factorial, which is equal to n factorial. And then we have proved an important result related to NPR, or NPR is equal to n times n minus 1 p r minus 1. So we can prove this result using the formula, or we can prove it using fundamental principle of counting. So these are the results that we have discussed in lecture 1. Let us look into the first problem, and the statement of the problem is like this. Find the number of permutations of 4 distinct objects taken 3 at a time. And this is a direct application of the formula. The formula that we have is number of permutations of n distinct objects taken r at a time is NPR is equal to n factorial upon n minus r factorial. Here our n is equal to 4 and r is equal to 3. Therefore, number of permutations of 4 distinct objects taken 3 at a time is equal to 4p3. If you want, you can expand it. 4p3 is equal to 4 factorial upon 4 minus 3 factorial. So no need to expand what is 4 factorial and what is 4 minus 3 factorial. You can just leave the answer as it is, or you can just leave the answer as 4p3. So this problem is a direct application of the formula that we have for NPR. Number of permutations of n distinct objects taken r at a time is going to be NPR, which is equal to n factorial upon n minus r factorial. Here the question is number of permutations of 4 distinct objects taken 3 at a time. Therefore the answer is equal to 4p3. So in all these problems related to permutations and combinations, I encourage the students to write the statements like this in the answer. So if you write the statements like this, then you will have a clarity. So if you don't write the statements like this and just write the answer as 4p3, still it is correct, but you cannot solve many problems. So I encourage the students to write the statements like this. Okay, let us move on to the second problem. So this is the second problem. Find the number of 4-letter words that can be formed using the letters of the word equation. So the statement of the problem is find the number of 4-letter words that can be formed using the letters of the word equation. And there are 3 more questions here. So how many of them start with E, how many of them end with N, and how many of them start with E and end with N. So on the whole, there are 4 parts in this question. The first part is find the number of 4-letter words that can be formed using the letters of the word equation. So let me write the solution. So before going into that, we have the word equation. So in this we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 distinct letters. Equation contains 8 distinct letters. Now the first question is number of 4-letter words that can be formed using the letters of the word equation. Number of 4-letter words that can be formed using the letters of the word equation is 8p4. So the number of distinct letters that we have is 8, and the number of 4-letter words that we have to form is equal to 4. We have to form 4-letter words. Therefore the number of 4-letter words that can be formed using the letters of the word equation is 8p4. Okay, now let us move on to the first part. What is the first part? The first part is how many of them start with E. The second part is how many of them end with N. And the third one is how many of them start with E and end with N. So whenever you have problems like this, you have to first satisfy the constraint. So the first question is how many of them start with E. So whenever you have a constraint like this, so what you have to do is you have to first satisfy the constraint. You have to first satisfy the constraint means we have 8 different letters. Equation. And we have to form 4-letter words. 1, 2, 3, 4. Now here the constraint is these 4-letter words should start with E. So what I do is I divide this work into 2 parts, W1 and W2. So W1 is to fill the first letter and W2 is to fill the remaining 3 letters. Here the constraint is we have to fill the first letter with E. Therefore the number of ways of doing W1. Number of ways of doing W1 is equal to 1. Why the answer is 1? The answer here means number of ways of doing W1 is equal to 1 because we have only one E and the number of ways of filling this blank with one E is equal to 1. Okay, after filling the first blank with E, so we will be left with 7 different letters. The 7 different letters that we have is Q, U, A, T, I, O, N. So these are the 7 different letters that we have. Now you have 7 different letters and you have to fill 3 blanks. Number of ways of filling these 3 blanks using 7 different letters. That means number of permutations of 7 different letters taken 3 at a time. So this number of ways of doing W2 is equal to W2 is equal to 7p3. Therefore the total number of ways of completing the task is equal to cardinality of W1 times cardinality of W2. which is equal to 1 times 7p3. So the answer is 7p3. So if you want, you can expand 7p3. 7p3 is nothing but 7 times 6 times 5, which is equal to 210. So the number of 4-letter words that begin with E is equal to 210. Let us look into the second one, that is how many of them end with N. Now we have 8 distinct letters and we have to form 4-letter words. Out of those 4-letter words, how many of them end with N? That is the question. So we have these 4 blanks. Now I am dividing this task into 2 works. W1 is to fill the last blank, W2 is to fill the remaining 3 blanks. Now the last blank should be filled with N. So W1 can be performed in only one way. After filling the first blank with N, the letters that we are left with are E, Q, U, A, T, I, O. So we have 7 letters. So here we have 7 distinct letters and we have 3 blanks. Now the number of ways of filling these 7 letters in these 3 blanks is going to be 7p3. So W1 can be performed in only one way, W2 can be performed in 7p3 ways. Therefore the number of ways of completing the task, number of ways of doing W1 is equal to 1. Number of ways of doing W2 is equal to 7p3. So number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2, which is equal to 1 times 7p3, which is equal to 7p3. Number of words that begin with E is 7p3, which is equal to 210, and number of words which end with N is equal to 7p3, which is also equal to 210. Now let us move on to the next part. The next part is how many of them start with E and end with N. Now many people will write the answer as 7p3 plus 7p3, but that is not the correct answer. Why that is not the correct answer, we will see. Suppose in your class, if 10 people got A plus in mathematics and 10 people got A plus in physics. Now how many people got A plus in both mathematics and physics? Definitely the answer is not going to be 10 plus 10. So if the answer is 10 plus 10, that is the mistake that you are doing here also. Okay. Now what is the constant here? We have to fill the first blank with E and last blank with N. The first letter should be E and the last letter should be N. So I am dividing this task into 3 works, W1, W2 and W3. W1 is to fill the first blank with E. W2 is to fill the last blank with N. W3 is to fill the remaining 2 blanks with the remaining letters. So if you fill the first blank with E and last blank with N, then the letters that we are left with are Q, U, A, T, I, O. So we have 6 more letters. Now the number of ways of doing W3 is going to be 6p3. Sorry, 6p2. So we have 6 distinct letters and we have to fill these 2 places. Now W1 is to fill the first place with E, which can be done in only one way. W2 is to fill the last place with N, and which can be done in only one way. Now W3 is to fill the remaining places with remaining 6 letters. Therefore, number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2 times number of ways of doing W3, which is equal to 1 into 1 into 6p2, which is equal to 6 times 5, which is equal to 30. So the number of words which begin with E and end with N is going to be 30. If there are no constraints, then the answer will be big. As we keep on increasing the constraints, the answer will be small. So on the whole, there are 210 words which start with E and 210 words which start with end with N. But there are only 30 words which start with E and end with N. Next, we have an interesting result. Number of permutations of end objects taken R at a time, which always contain a particular object, is going to be R times n minus 1 p R minus 1. So let me explain the question using some example. Okay. So let me take the previous question itself. Suppose we have this equation EQUATION. Now number of 4-letter words. If I ask you this question, number of 4-letter words is equal to 8p4. Now I am not interested in this question. I am interested in how many of them contain Q. This is a question that I am interested in. So in the previous question, this line, we have number of permutations of 8 distinct objects taken 4 at a time is going to be 8p4. I am not interested in this one. I am interested in how many such permutations contain Q. This is the question. Now if we can able to answer this question, then we can able to answer this generalized version. Okay. Now our task is to fill these 4 blanks, 1, 2, 3, 4. Now what is the constraint we have? The constraint we have is it should always contain Q. It should always contain Q. Now what you can do is you can fill this Q first. But here there is one doubt. So where we have to fill this Q? I can fill this Q in the first place or second place or third place or fourth place. So I am dividing this task into 2 tasks, W1 and W2. W1 is to fill Q and W2 is to fill the remaining 3 places. Now in how many ways we can fill Q? We have only one object, that is Q. Now I have to fill this Q in one of these 4 blanks. So how many options are there for Q to sit in these places? Q can be placed in first blank, or Q can be placed in second blank, or Q can be placed in third blank, or Q can be placed in fourth blank. Therefore the number of ways of completing the work W1 is going to be 4. Now after completing this work W1, so from the letters of the word equation we have already filled Q. After filling Q, the letters that we are left with are U, A, T, I, O, N. So we have these 7 letters. Now how many places we have? So we have actually 4 places, but we have filled these 4 places with 1 Q. After filling these 4 places with 1 Q, we will be left with only 3 places. We will be left with 7 letters and we will be left with 3 places. Therefore, the number of ways of completing W2 is going to be 7P3. Number of ways of completing W2 is going to be 7P3. Now the total number of ways of completing the work is going to be 4 times 7P3. So this is the answer. Now we can generalize this result. If we generalize this result, then we will have this one. Number of permutations of n distinct objects taken are at a time which always contain a particular element. So let us answer this in a fresh page. Okay. Now we have n distinct objects. Okay, let me write down those objects. 1, 2, 3, so on up to n. But out of these n distinct objects, this is my special element. I always want this special element to be there in my permutation. And how many blanks we have? R blanks. Now we have n distinct objects and we have R blanks. Our task is to fill these R blanks using these n distinct objects. So in general, the answer is going to be NPR if there are no constraints. But here we have a constraint. What is the constraint that we have? We want this special element to be there in this permutation. Now I can keep this special element in one of the places. Now let me write down that one. I am dividing this task into 2 works, W1 and W2. W1 is to fill the special element. In one of the R places. W2 is to fill the remaining R minus 1 places with n minus 1 objects. So on the whole we have n objects. Out of those n objects, I am taking this special object and filling this special object in one of the blanks. So I will be left with only n minus 1 objects and I will be left with only R minus 1 blanks. Now number of ways of doing W2. Number of ways of doing W2 is equal to n minus 1 P R minus 1. And number of ways of doing W1 is equal to R, because I can place this element in the first place or second place or third place or rth place. So this element has R chances or R options. Therefore the number of ways of filling this element is equal to R. Now the total number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2, which is equal to R times n minus 1 P R minus 1. So this is the precise proof of this statement. We have proved this result. Number of permutations of n objects taken are at a time which contain a particular element is R times n minus 1 P R minus 1. I can explain this result using some example. Now I have this word equation. Now let me ask 4 questions. How many 4-letter words begin with E? I think we have done this question, therefore the answer is going to be 7P3. So why we have this 7P3? On the whole we have 8 letters. 8 we have to fill these 4 blanks. So we have to fill the first blank with E. After filling the first blank with E, we are left with 3 blanks. And we are left with 7 objects. 7 objects and 3 blanks. Therefore the number of ways of filling these 3 blanks using these 7 objects is going to be 7P3. Let me ask the second question. How many 4-letter words contain E in second place? Now, in order to answer this question, we have to fill E in the second place. After filling E in the second place, we are left with 3 blanks. And we are left with 7 letters. So the number of ways of filling these 3 blanks using these 7 letters is going to be 7P3. Now the next question is, how many 4-letter words contain E in third place? So which is again going to be 7P3, because we have to fill these 3 blanks with 7 letters. So similarly the fourth question, how many end with E? End with E means we have to fill the last blank with E. After filling the last blank with E, we are left with 3 blanks and we are left with 7 objects. Therefore the number of ways of filling these 7 objects is, 3 places is 7P3. Now let me ask an interesting question. Now how many words contain E? How many words contain E? How many words contain E means E can be in the first place, or E can be in the second place, or E can be in the third place, or E can be in the fourth place. Now how many words are there which starts with E? Is going to be 7P3. Now E in the second place is going to be 7P3. E in the third place is going to be 7P3. E in the fourth place is going to be 7P3, which is equal to 4 times 7P3. This 7 is nothing but 8 minus 1, P 4 minus 1. Total number of objects is 8 and the number of places is going to be 4. Therefore the answer is 4 times 8 minus 1, P 4 minus 1. Or in general the answer is R times N minus 1, P R minus 1. Next we have an interesting theorem. If n comma r are positive integers with 1 less than or equal to r less than or equal to n, then npr is equal to n minus 1 pr plus r times n minus 1 pr minus 1. So no need to get panic with this result. So if you know how to read each and every term in this expression, we can answer this question immediately. Now what does NPR stands for? NPR stands for number of permutations of n distinct objects taken R at a time. And just now we have seen what does R times n minus 1 PR minus 1 stands for. R times n minus 1 PR minus 1 stands for number of permutations of n distinct objects taken R at a time, which always contain a particular element. Now what does n minus 1 PR stands for? N minus 1 PR stands for number of permutations of n minus 1 objects taken r at a time. Okay, so we can give the proof of this one. Okay, let me write a small statement. Number of classes which I took is equal to number of classes in which you are absent plus number of classes in which you are there. The total number of classes which I took is equal to number of classes in which you are absent plus number of classes in which you are present. Now we have n objects. So assume that we have n distinct objects. Now we have this special object. Now how many permutations we can have? The total number of r digit permutations we can have is npr. Now number of permutations which do not contain that particular element, which do not contain that particular element. Which do not contain that element means we can remove that particular element. I am removing this one. So total number of objects is going to be n minus 1. And number of places is equal to r. Therefore number of permutations without that element is equal to n minus 1 PR. Now number of permutations which contain that element is equal to r times n minus 1 PR minus 1. So this implies total number of permutations that is NPR is equal to n minus 1 PR plus r times n minus 1 PR minus 1. So this is the proof using combinatorial argument. So those who are not interested in this combinatorial argument, they can give the proof using formula. But I recommend students to give combinatorial arguments in permutations and combinations. So if you start giving combinatorial arguments to give the proofs for sub statements, you can get hold of permutations and combinations easily. Anyway, we can look into the result using the formulas. Now we have NPR, we have to prove NPR is equal to n minus 1 PR plus r times n minus 1 PR minus 1. So let me expand this RHS. So n minus 1 PR is nothing but n minus 1 factorial upon n minus 1 minus r factorial plus r times n minus 1 factorial upon n minus 1 minus of r minus 1 factorial. So which is equal to n minus 1 factorial upon n minus r minus 1 factorial plus r times n minus 1 factorial upon n minus r factorial. So from these two terms I can take n minus 1 factorial common. And coming to this n minus r factorial, I can write n minus r factorial as n minus r times n minus r minus 1 factorial. So on the whole I can take n minus 1 factorial upon n minus r minus 1 factorial common. So I will have 1 plus r upon n minus r. So which is equal to n minus 1 factorial upon n minus r minus 1 factorial into n minus r plus r by n minus r, which is equal to n minus 1 factorial into n upon n minus r minus 1 factorial into n minus r. This n minus 1 factorial times n, you can write it as n factorial, and n minus r minus 1 factorial times n minus r, you can write it as n minus r factorial. Therefore the result is n factorial upon n minus r factorial, which is nothing but LHS. So NPR, you can write it as n minus 1 PR plus r times n minus 1 P r minus 1. So this is the result that we have proved. So this is the proof using formula. Okay, now let us look into the next problem. Find the number of 4-letter permutations that can be formed using the letters of the word mixture. How many of them contain X and how many of them do not contain X? Solution. So we have the letters of the word mixture, M-I-X-T-U-R-E. So how many are there? 1, 2, 3, 4, 5, 6, 7. So on the whole we have 7 objects. 7 distinct objects. Now number of 4-letter permutations. Number of 4-letter permutations is going to be 7p4. So these are the total number of permutations without any constraint. Now we have the first problem. So what is the first problem? Which contain X. We have to find total number of 4-letter permutations which contain X. Now we have this formula. Number of permutations which contain a particular element is r times n minus 1 p r minus 1. Here n is equal to 7 and r is equal to 4. N is equal to 7 and r is equal to 4. Therefore number of 4-letter words which contain X is equal to 4 times 7 minus 1 P 4 minus 1, which is nothing but 4 times 6p 3. Now coming to the second question. The second question is which do not contain X. So you can answer this question in 2 ways. So the first way is total number of permutations, total minus number of permutations which contain number of permutations which contain X. So the total is 7p4 minus 4 times 6p3. So you can answer it in this way, or else you can answer this question in this way. So which do not contain x. We have these letters of the word mixture. So what you do is remove x. So if you remove x, what we have? M-I-T-U-R-E. Now how many letters are there here? 6. And how many? And the requirement is we have to form 4 letter words. So which is nothing but 6p4. Both the answers are correct. So if you want, you can cross check. You can expand these things and you can expand this one, and you can check both the answers give the same number. Okay. Now let us look into this next problem. In how many ways we can arrange 5 boys and 4 girls in a row? And there are 2 constraints here. The first constraint is the row should begin and end with a boy, and the next one is it should begin with a boy and end with a girl. So let us write down the information. The information is we have 5 boys and we have 4 girls. First, let us answer this question without any constraints. So number of ways of arranging these 9 people is equal to 9p9, which is nothing but 9 factorial. So these are the total number of permutations without any constraints. So let us look into the first constraint. The first constraint is it should begin with a boy and end with a boy. Begin and end with a boy. So what we do here is we have to start with a boy, and we have 9 places, 1 2 3 4 5 6 7 8 9, and we have to end with a boy. Now the task is to fill these 9 places with 5 boys and 4 girls, but in this task we have some constraint. The constraint is we have to begin with a boy and we have to end with a boy. So I am dividing this task into 3 parts. W1 is to fill the first place with a boy, and W2 is to fill the last place with a boy, and W3 is to fill the remaining places with the remaining people. So let us write down what is W1, W2 and W3, and then we will count these things. W1 is to fill the first place with a boy. This you can do in 5 ways. And W2 is to fill the last place with a boy. So after filling the first place with a boy, we will be left with only 4 boys. Therefore, the number of ways of doing W2 is equal to 4. After filling the first place with a boy and last place with a boy, we will be left with 3 boys and 4 girls. Three boys and 4 girls. Now we can fill the remaining 7 places. This implies number of ways of doing W3 is equal to 7p7, because we have 7 people and we have 7 places. Number of ways of arranging these 7 people in 7 places is equal to 7p7. Or we want to take all the objects, therefore npn, which is equal to 7 factorial. Okay. Now the total number of ways of completing the work. total number of ways of completing the task is equal to number of ways of doing W1 into number of ways of doing W2 into number of ways of doing W3, which is equal to 5 into 4 into 7 factorial. So with this we have completed the first part. Now the second part. Begin with a boy and end with a girl. So again I am dividing the task into 3 parts. W1 is to fill the first place with a boy, W2 is to fill the last place with a girl, and W3 is to fill the remaining 7 places with the remaining people. Now the number of ways of doing W1. Number of ways of doing W1 is equal to 5 because there are 5 boys. Number of ways of doing W2 is equal to 4 because there are 4 girls. And number of ways of doing W3 is equal to 7p7 because after filling the first place with a boy we have 4 boys, and after filling the last place with a girl we have 3 girls. So on the whole we have 7 people. So in how many ways we can arrange these 7 people in these 7 blanks? It is 7p7, or which is 7 factorial. Therefore the total number of ways of completing the task is equal to 5 times 4 times 7 factorial. So all that you have to understand from this example is to implement the constraints. So in the first question, in the first part, we have to fill the row with a boy and we have to end the row with a girl. In the second part, we have to begin the row with a boy and we have to end the row with a girl. So first you have to impose the conditions. After imposing the conditions, we are free to choose. So here the conditions are imposed on only W1 and W2. W3 we can choose anything. So similarly here also the constraints are there on W1 and W2, and there are no constraints on W3.